Hello class, welcome back. In this video we are going to go through chapter 6.2, real applications of normal distributions. So in the last section we kind of touched on what a standard normal distribution is. Now we are going to take that and apply it to data that we might get in the real world. So we know that in order to use the z-scores, the mean must be 0 and the standard deviation must be 1. However, you would never get that in real life, no matter what you're doing. So say your normal distribution is weights of babies or heights of males or wait times at a restaurant. No matter what it is, you're not going to get a mean of 0 and a standard deviation of 1. So therefore, we need to standardize any normal distribution. This is our way of applying one solution method to all normal distributions. So think of it as if you have all these different normal distributions based on all your different things that you're analyzing. Well, to compare those would be apples and oranges. But by having a standardized normal distribution, now we can compare apples to apples. So we are converting a normal distribution into a unit density curve so we can utilize the z-scores. So the conversion formula, and this is one that you will have to use, z equals x minus mu over sigma. So z equals the x value minus the mean over the standard deviation. And this is the formula we use to allow us to standardize any normal distribution so that x values can be transformed to z-scores. And we know how to use the z-scores, and then you can scale it up to your problem. So to put this in a graphical form, you have your non-standard normal distribution, which whatever thing you're looking at. So let's just say weights of babies, you have your mean, and then you're looking at x, which is just any value away from your mean, and now you apply this formula and boom, you have a standard normal distribution, which you can now use to calculate probabilities based on your z-score. So procedure for finding areas with a non-standard normal distribution. First, it helps to sketch the normal curve, label the mean and any specific x values, and then shade the region that you are trying to find the probability of. And then for each relevant value x, you apply the formula to it, and then we use technology or the table to then find the probability of the shaded region. So these are the same slides from the previous section, just about how to find how to find probabilities using a z-score. So I'm not going to go through them again, and we're going to go straight to an example problem. So the example problem is, what proportion of men are taller than the 72-inch height requirement for shower heads? So we are assuming that heights of men are normally distributed with a mean of 68.6 inches and a standard deviation of 2.8. Find the percentage of men who are taller than a shower head at 72 inches. So step one, we're gonna draw it out. So we have our normal curve, we have our mean value of 68.6, and the critical x value that we are looking at is 72. And we want to know what this shaded region is over here. Well, a way to do that is we would have to find our corresponding z-score. So we know our mean, we know our x value, so we plug it into this formula with our standard deviation. Boom, we get a z-score of 1.21. Then we could use that. You can use any of the methods you want to find what that probability would be. So one thing to remember is that in this score, we are looking for probabilities greater than 72. So when you use the table, you get all the values equal to or less than. So if you want to know what's to the right of the curve, you would just have to do 1 minus that value. Next is finding values from known areas. So just some helpful hints for you. It really does help to draw a graph to kind of visually understand what you are looking at. It's a little harder to just do it all in your head. Another area of error is people often confuse z-scores and areas. So remember, z-scores are the distance along the horizontal axis. Those are how many standard deviations away you are. So remember, in a standardized normal, the standard deviation is 1. So a z-score of 1 is 1 standard deviation away. But the areas are what the body of the table represents. That's the area under the graph. So you draw that vertical line straight from your z-score that you are currently analyzing, and then you look at the area to the left of it, and the area under that curve is what the probability is. Another common thing to note, another common error is making sure you're looking at the right side of the graph as well. You know, if you top 10% will be located to the right side of the graph, but a value separating the bottom 10% will be located to the left. Think about the last example we did from the previous section. Z-scores to the left of the mean would be negative, and the areas are always going to be between 0 and 1, and they can never be negative. So how to solve these problems? First, you will sketch your normal distribution curve. Use technology to find what your corresponding probability is. And then if you know your z-score must convert to the equivalent x value, you can use the conversion formula below to find what your corresponding x value is. And we're going to do an example to kind of help solidify that equation. Just another way of wording it. So let's look at the example. I hate giving equations without an example. So when designing equipment, one common criteria is to use a design that accommodates 95% of the population. We have seen that only 46% of women satisfy the height requirement for the U.S. Air Force pilots. What would be the maximum acceptable height of a woman if the regulations were changed to allow the shortest 95% of women to be pilots? That is, the 95th percentile of heights of women. So if you're greater than 95%, you would not be able to be a pilot. So the shortest 95%. Assume that the heights of women are normally distributed with a mean of 63.7 and a standard deviation of 2.9. So step 1, we're going to just draw it out. So the figure below shows a normal distribution with the height of x we want to identify. So 63.7 is our mean, and we want to know what this x value is. And we know the area underneath would be 0.95 because it's the shortest 95%. So this white region under the curve would be 0.05, and this would be 0.95. This is just this hand sketch. So we can use our formula to figure out what this z-score is and then kind of reverse engineer it using the formulas we have given. We could also use technology to provide the value of x. You can do this in Excel also. So if you know your probability, you know your mean, you know your standard deviation. So in a cell, you'll type in norm period INV. It'll kind of come up automatically. And then they want it in this format. So you do your probability, comma, your mean, comma, your standard deviation, close parenthesis, hit enter, boom. You get your 68.47. You could also solve this using the z-tables. So we know that the area is going to be 0.95. And we want to, so we find our corresponding z-score using the equation, since that would be the unknown, and we know the rest of them. So once you know that the z-score will be 1.645, we can then use the tables. So the area 0.95, you look at the chart, and then you see that it corresponds to that value. Using the equation, so on and so forth, and you can get x from this way as well. And you can see that this 68.47 is the same value that we got using Excel. So both methods work. Shocker. And that's it. That was just kind of going through some examples. Thank you.